Okay, welcome everyone. So this video is a continuation of or some kind of continuation of the videos I've been doing before on building of LLM. First of all, I would like to point out that I'm really sorry that I won't be able to really continue it in a more tutorial manner because school has resumed, and since I'm working and also schooling, so it's kind of hard to really make the videos in a more tutorial manner, though I'm still devoted to learning and building up my skill till I'm able to read and implement research papers. And as a continuation from my previous videos, where I kind of made a tease, how do you call it, a kind of teased on the version 1 of this LLM. So I've done the version 2 of it, which is just a little improvement on the version 1. But since I didn't really talk fully on the version 1, so I want to kind of continue from there. So this will be what I'm about to do, will just be a brush through of the implementation. So what we have here is a very tiny large language model, character level tokenization with only one attention layer and one feed-forward layer. It doesn't follow the standard structure of a transformer for a kind of state-of-the-art model. So what we have here is just a very basic one that understands only characters. So it understands the character, unlike a standard LLM that understands words or tokens that are in almost full words. This one only understands character. So the first thing here is that I define the training data. So the training data is a very little piece of text. So this model is meant to be very small, but it helped me learn all the sorry, it helped me learn all the very basic parts of an LLM. So I was able to learn all the basic part of an LLM. And so this the training data. So the first thing we do is, remember, the most important thing in an LLM is the token. So to prepare this model, the first thing is we obtain the token. And since we are just doing it with a small piece of text of the English language, there's no need for us to try and get the full everything that makes up the English language or get a full token of everything. So the first thing I do is I get all the unique this thing. Let me use this is the first Python file I wrote. Let me use the one with more appropriate naming. This was the initial one that I was trying to make sure it works. Okay, so the very first thing I do is, it's the same thing. So the very first thing I do is I get the unique characters that make up the training data. So in this training data, I want to get every single unique thing, the Q, the U, the I, and the T. So after getting it, I sorted it. This step is actually not very necessary, but sorting it helped with representation, like when I printed it out to see what it looks like. So it helped that manner. And we want to have a set of data that we can train the model with. And the way training works is that we have what we want to show the model and what we expect the model to see. So the way we are going to be dividing this will be like this. So what we aim to achieve is that that has a certain length, and then we also have an output that has the same information but with an extra one, like this village here. So the goal here is that when we give the model once upon a time in a small, the model will produce an output. So if that output is not village, or at the beginning the output definitely will not be village, it will be total rubbish. So the model produces an output, and then whatever nonsensical output it produces, whenever you see once upon a time, you should produce once upon a time in a small village. So when we keep repeating this, going through the full text, like for example, we pick a certain window starting from ones to small, and then from there we increase them one word at a time. So that's basically what we'll be doing. So this is the text. So let's say this is the text. We have the context window of the model moving over the text in this manner. So for any particular time, it sees only the set of characters that are in this window. And this window now is called the context window of a model. The amount of text, the amount of token the model can see at any particular time. So that's what we want to achieve. So to achieve that, we first of all create a map. So this map now is so that we will be able to convert our actual characters to token ID. Remember that a token does not want to see the token in terms of text, but it understands only the numbers that represent it. So that's what we want to achieve here. So after sorting the token out, we will now create a map, like a dictionary, a Python dictionary, that maps each character to a number. So in this case, whatsoever number they represent in this set is index. The same thing here. Sorry, not the same thing. So after getting this is to character, why we are doing this is that this particular dictionary will be used. This particular dictionary will be used to fetch the index whenever a character is provided, while this particular one will be used to fetch a character whenever an index is provided. And these are the functions that will be doing the actual job. So the encode means take a character and give me the index, so it encodes it. While the decode means takes an index or a list of index in this case and return the characters that represent it. So after that, we specify the context window of the model. So I would like to mention that the code is on GitHub and you can go and study it yourself. So after that, we have the context window, and what I call here the feature list here is basically what will be given the model during training, while the target list is what will be showing the model after it has produced any stupid output. We'll now tell him, okay, this is what we were supposed to produce. So this one will be a list of the input that will be given in, while this one will be a list of outputs that will be showing the model in the training process. So to form this list, to fill in this list, we go through the training data, like what I showed you earlier, what I was context window around the training data. It goes through the training data, filling in the two lists in the manner I've explained earlier. Then after that, after we've gotten the list, we are not going to be using Python array, or the models do not work well with Python arrays. So they work well with tensors. So tensors are just arrays that we can have multi-dimensional form. And then it also gives the ability for operations to be done on it with the help of GPUs. So like it is optimized for GPUs. That's what I mean to say. And then here we will now specify the maximum length. So we'll specify the maximum length of the input that the model will see, and then we go on to define the transformer itself. So how the programming of the transformer works is that, first of all, you kind of do all the settings for the transformer, which is what we do in this constructor here. So everything here is just kind of the initial setup. So what happens is that the first thing we do is we set up the token embedding. matrix. So the token embedding matrix is a learnable weight that the model uses to fetch that the model uses to fetch information about a particular token. Remember, when a sequence of token enters a model, the very first thing that happens is that the model fetches their ideal meaning. Like, let's say a set of words like a boy enters the model. Before the model thinks of completing the sentence where we have a boy in it, the model first of all fetches the default meaning of a boy from its embedding matrix. So after fetching the default meaning of a boy, and then knows that okay, a boy normally represents a young male human being. It is from there that the model will now use that default meaning, and with the help of whatsoever words surrounding the boy, to understand the context where the boy is placed, and then uses that to predict up the next tokens that will come up. So that's how it works, and this is the embedding metric. So this is where the default meaning of tokens are stored, and then the positional embedding metric. So this one tracks the position. Remember that a transformer model processes all the tokens that make up a sequence simultaneously. So swapping of positions does not affect the model, and the model doesn't know anything about the position. So it sees it sees the sentence, the boy is a man and the man is a boy. Sorry for that bad example, but that's what just came to my head. So the boy is a man and the man is a boy as the same thing. Why? Because all of them contains the exact same word. So it doesn't understand the position. That's why we have a separate matrix. The next thing we do is we define the attention layer. So for the attention layer, just like I mentioned earlier, we are going to have only one attention head. So a good way to picture this is to picture a cuboid. So for a cuboid, we have the length, the height, and the width. So the way data will be flowing through this transformer is that the height of the vector which represents the data will be the number of embeddings. Then the length will be the maximum length of sequence, while the width will be the batch size. So that's a way to picture it. And then we now specify the feed-forward network. So for the feed-forward network now, once the model reaches the point of feed-forward, so it enters with the size of n embed, but as it is there, it is expanded to 4 times its original size, so that the model will have the room to explore different combinations of the token, 3 signals, and then from there it now passes through what it entered the model as. And then we now have the last part of the data, which was flowing with the size of number of embedded, and then reduces back, transforms it to the vocabulary size. So the vocabulary size here is why it is done this way is because, remember, in the model, the model doesn't automatically just predict the exact token. It produces the full dictionary list of every token that the model understands, and then assigns probabilities to it. So we can now choose the ones with the highest probability, or maybe vary it a little. That's why for any output that is coming out from the model, the final thing that comes out is always of size. It's always of the same size with the vocabulary, which is a dictionary of all the possible tokens the model can understand. And then how is the feed forward? Sorry. So the next thing I have here is how the feed forward process will look like. which is the text from the user that the user wants to autocomplete. So once it comes in, just like I said, the first thing that is done is the default meaning of it is fetched. So after fetching the default meaning of the tokens there, we now use this to get the positions of the token. So we now get the positions of the token. We then add the two of them together, the position and the token embedding, to have one vector that is going into the network. So we now define the mask. We do not want the model to kind of peek into the future. Remember, a transformer model sees everything in the sentence simultaneously. So during training, we do not want the model to be able to kind of see into the future. We want it to produce the next token based on what it has seen before. So we mask the attention pattern. So masking the attention pattern, we define what the mask will look like. So for the mask now, the mask will be number of, and then we'll be using the same device as the input feature. And then another thing is, remember, we want to set everything to true. And so that's for the masking. Then the next thing is the attention layer. So for the attention layer, we now send in the feature tensors. Like, remember, in the attention layer of a transformer, we have the key, the value, and the query metrics. So we send in the feature tensors that will represent each of these. So the feature tensors for each of these, that's why we have 3 of it here. And then we also pass in the mask that will be used. A good way to visualize the masking is just, though it is not really that way, but it's more like the mask is a kind of veil that is placed on top of the portion of the attention pattern that we don't want the model to use. So after passing everything, like here we are, is added back to the feature tensor. So this and then what we get is then fed into the feed-forward network. So what I want you to really notice here is that the first thing is the data or the vector goes through the attention layer. From the attention layer, we add back the initial input. We now feed the result into the feed-forward network. Once what we get there, we still add back the feature tensor again, and then we now feed it back. The feed-forward network will work, and then after that we instantiate the transformer class. So after instantiating the transformer class, we also instantiate the optimizer. So this is so that after the weight has been trained, we'll just save the weight. And this so this function now is to save the weight of the model. Sorry, not down. So this function now is to save the weight of the model after training. So during the training now, we want the model to go through the training data 3,000 times. Ideally, this number of times, or as they call it, approaches, is too much. But while I'm doing it this way, so that the data can be overfitted into the model parameters, into the weight of the model, and we can have a meaningful prediction. For the size of the model we have now, we cannot get anything meaningful. It can't generalize. So the only thing we can actually achieve with this very little model is overfitting. So that's why I set it to 3,000 times, so that it perfectly overfits that list we prepared earlier. Remember when we prepared 2 lists, one that will be feeding to the model during training, and the other one that we will be showing the model for any prediction it makes. So we feed it in here, and then the output that comes out after everything happening here. The output that comes after everything happening there is then fed, is then used to calculate the loss. So the loss is just a measure of the difference between the expected output and the produced output. Then after that, we use the optimizer to perform back propagation so that the weight will be adjusted. So for each round of the training where we've reached, let's say 20, 40, or anything that is a multiple of 20, we print out the training of a model. This is the number you should be monitoring to make sure it is reducing. So we monitor if it is reducing, and then for any printout, we try to make a prediction, which we call inference. So we print it out to see how meaningful it is. So we keep printing that way to see how meaningful, like minus the idea of the loss going down. We also want to actually see if the model is actually getting better at the job, the function above. Then the inference now. So for the inference, we remember we saved the model, so that means we also need to load the model from where we saved it. So this code here is to load the model weight. In this case, once upon a time, which is part of the training data. If you check the training data, we have a sentence there called once upon a time. Once upon a time, we encode it of each of the character in that sentence, and then we create a tensor of it, because this is what models understand. So after creating a tensor of it, we now initialize the transformer class again. After initializing the transformer class, what we get there is now passed into this load model, so that it uses the information there to load the model. So after loading the model, we now start the model. Note here we are using the .eval method here. So this one tells the model that this is an inference process and not a training process. So for such processes like back propagating and adjusting of the weights will not be called, like they will not run. It is only the prediction alone that will run. So back propagation and adjustment of weights will not run. Why? Because we are telling the model it does what I mentioned. So no gradient, there should be no gradient. Basically, we don't need this thing here. So we now number of token as with the maximum number of token as where the model should stop. Remember, if a model is making a prediction, it doesn't just keep predicting, it stops somewhere. So this one here is when it should stop, and based on what I have here, it should stop after producing 100 extra characters added to the initial sequence that entered the model. So there are probabilities attached to all the tokens that make up the vocabulary size. So from here, basically what we do here is that we are picking those ones with the highest probability, which ensures that we produce something that is exactly what was on the training data. So after producing that, in each case, we add the extra data back to the initial sentence that entered the model, and then use that as completed, and then which are numbers. In order to produce something meaningful to the user, we will need to convert it back to characters, concatenation of characters, which then forms a sentence, and then we return the sentence and also print it out. So that's basically how it works. I'm very sure what I explained wasn't that clear, but for anybody that has a good knowledge of how a transformer works, there should definitely be some meaning in what I said. So that's for the very first model, the version 1. So the next video now will be the version 2, but I will have to stop here so that this particular video will not be too long.